Okay, now on to hypothesis testing. For some definitions, when we talk about a hypothesis in statistics, it's just a claim or some statement about characteristics of a population. And a hypothesis test, and sometimes it's called a test of significance, is just a process that we go through for testing one of these claims. And in this chapter, with the sections that we're covering, we're going to talk about hypothesis tests that have to do with either population proportions or population means. Here's some examples of hypotheses that we might want to test. First of all, in genetics, if we have an institute that claims that it has a method that allows couples to increase the probability of having a baby girl. In business, a newspaper headline makes the claim that most workers that get their jobs through networking. In medicine, medical researchers claim that when people with colds are treated with echinacea, the treatment has no effect. And in aircraft safety, the FAA claims that the mean weight of an airline passenger is greater than the 185 pounds, which it was 20 years ago. So the components of doing a formal hypothesis test. First of all, we have to have our hypotheses, and we have two of them, a null hypothesis and an alternative hypothesis. Then we have what we call a significance level, alpha, and this alpha connects right back to the alpha that we were talking about in the last chapter. We have what we call a test statistic, which is, in the case where we're using a normal distribution, it's really just a z-score that we get from our sample data. And we have two basic methods of conducting hypothesis tests. One is called the traditional method, and in that method we have to find critical values, similar to what we did with our confidence intervals. The other method is called the p-value method, so for that one we have to find p-values. And then we have an initial conclusion that tells us what we're doing with our hypotheses, and a final conclusion that actually states the conclusion in words in terms of the original claim. So first, our null hypothesis. In this class, the way we're going to conduct hypothesis tests, our null hypothesis always says that our population parameter is equal to some number. So it's always going to be an equal. And that's what we're going to be testing, is the null hypothesis. Our initial conclusion is going to be either to reject the null hypothesis or fail to reject the null hypothesis. The way that I like to think about this is, suppose that you're sitting on a jury and you're deciding whether to convict someone based on the evidence. You always want to err on the side of not convicting an innocent person. So the null hypothesis is similar to the assumption that the person is innocent unless they're proven guilty. So basically that's what we're going to stick with unless we have very strong evidence that tells us to reject that. So if we're failing to reject our null hypothesis, that tells us that there was not strong enough evidence. So this would be like saying there's not strong enough evidence to convict the person. We don't have strong enough evidence to convince us beyond a reasonable doubt. And one way you can remember this is that the fail and the not here go together. If we're rejecting the null hypothesis, that's basically saying we do have strong enough evidence to support our claim. This would be like saying we have strong enough evidence to convict someone. It does have to be very strong to get past that assumption of innocence. Now, the alternative hypothesis is going to be a statement that our population parameter has a value that's different from the null hypothesis. And in this class, again, our alternative hypothesis is going to have one of these three symbols, either a not equal to, a less than, or a greater than. It cannot have an equals with it. Here's an example. Let's consider the claim that the mean weight of airline passengers is less than 195 pounds, and we'll look at how we would find the null hypothesis and the alternative hypothesis. Well, first of all, if we're talking about a mean, then we're going to use mu because that's the notation we use to stand for our population mean. So this is the symbol we're going to use. And usually the easiest way to start out with this is just write down what you get from the claim. So our claim in symbols would say that our mean is less than 195 pounds. Now, if this symbolically doesn't have an equal sign, then we're going to use that for our alternative hypothesis. So we can actually go ahead and write down our alternative hypothesis is that mu is less than 195. Once we have the alternative hypothesis, all we have to do to get the null hypothesis is take the same symbol, the same number, and just replace our inequality with an equal sign. Now, when we talk about our significance level, this is alpha, just like we used when we were doing confidence intervals. But in hypothesis testing, we usually talk about the alpha directly. So we'll say it has a significance level of 0.05 or 0.01 or 0.10. Those are three very common ones. Our test statistic comes from our sample data, and as I said earlier, this is basically going to be like something like a z-score that we get from our sample data. So it tells us how extreme our evidence is, or how strong our evidence is from our sample. Okay, so here briefly are our formulas for our test statistics, and we'll talk about these again in the specific sections where we're talking about the different kinds of hypothesis tests. So just really quickly, when we're testing a claim about a proportion, this is the test statistic that we use. And the thing to notice here is that we have a z here, which tells us that we're using our normal distribution. If you're using a table, that means you're going to be using the z-scores table. And here's the test statistic formula if we're testing a claim about a population mean. And notice that this one has a t instead of a z. And again, that means that we'll be using that t table in the statistics textbook. So let's go back and look at an example. In this one, we had our gender selection method. The claim is that it increases the likelihood of having a baby girl. Some results from a test of this method involve 14 couples who gave birth to 13 girls and 1 boy. So we're going to test that. We're going to use the claim and these sample statistics to calculate the value of our test statistic. All right, so first we want to think about what are our hypotheses. And we would assume in the first place that the likelihood of having a baby girl would be 50%. So if we're increasing the likelihood of having a baby girl, then we would want to know that it was more than 50%, or as a proportion it would be more than 0.5. So our alternative hypothesis is going to be that p is greater than 0.5. And that means, again, for our null hypothesis, we're using the same symbol, p, the same number. We're just replacing the inequality with an equal sign. So there are our two hypotheses. Our sample proportion is 13 out of 14 because we're considering a girl a success. So there were 13 successes out of our 14 trials. In decimal form, that's 0.929. So if we use those numbers and plug them into our test statistic formula, remember the p with the hat comes from the sample. So this is our sample proportion. The p without the hat comes from our null hypothesis. So that's just the number that was in our null hypothesis. Same with this p down here. And the q here is just 1 minus p. The n is our sample size. So here's where all those numbers would go in, and that gives us a test statistic of 3.21. And remember, since this is a z, this would be our standard normal distribution. So, and remember that a 3 or above is a pretty high value for a z-score. Now, one method of doing hypothesis testing is to use critical values and critical regions. And these critical values are similar to what we used with confidence intervals. What we do is we find them and use them to draw a picture of our distribution and then shade in certain regions, and that's what we call our critical region. So there are 3 different ways that we do this depending on what type of test we have. The type of test depends on what our alternative hypothesis has for its inequality. If it's a not equal to, then that automatically makes it a two-tailed test. And what this means is that we'll treat this just like we did with confidence intervals. Our alpha is going to be divided in half equally between the two tails of our distribution. So here's what our picture would look like. Over here on the right tail, our area would be alpha over 2, just like it was for confidence intervals. We'd have another alpha over 2 over here. And it's always the tails for hypothesis tests. It's always the tails that are going to be our critical regions. So these two parts where we have the alpha over 2 and the two tails are going to be our critical regions. And what that means is that if our test statistic is in one of these two regions, then our conclusion will be to reject the null hypothesis. On the other hand, if it's in the middle between those two, then our conclusion will be fail to reject the null hypothesis. Now again, if we look at our alternative hypothesis, if our inequality is a less than, so if it's pointing to the left, then that tells us automatically that we have a left-tailed test. And we know that again because the inequality points to the left. What we do in this case is that we put all of our alpha over in the left tail of our distribution. So this area here is all alpha. In other words, there isn't any over on the right end. So in this case, our critical region would be just this left tail. That's where we would reject the null hypothesis, and in the rest of our distribution we would fail to reject. And the last one is a right-tailed test. And again, we can tell this because in our alternative hypothesis, our inequality points to the right. And that means that we put all of our alpha over here in the right tail. And this is our rejection region, or our critical region over here, which means that we would reject the null hypothesis. So let's look at a couple of examples. Going back to our gender selection method, we had our null and our alternative hypotheses already. Notice our alternative hypothesis had a greater than, which points to the right. That tells us right away that we have a right-tailed test. And again, that's because we had a greater than. So what we would do in order to find our critical value is that we would go back and see what alpha was. Alpha was 0.05. That means we want to have 0.05 as an area in the right tail of our distribution. So we want this area right here to be 0.05. And what we're looking for our critical value is what's our cutoff value for z. Now, if you remember, when we use our z-table, the z-table goes from a value to the left, not from a value to the right. So in order to use our z-table for this, we're going to have to figure out what the area is to the right of this cutoff value. And it's just going to be 1 minus our alpha. So it's going to be 1 minus 0.05. So that's going to be 0.95 or 0.9500. So if we're using our table, then what we would do is look up 0.9500 in the middle, of our table, find the value that's closest to it, and then find the corresponding z-score. And in your table, you're going to get something that looks like either 1.64 or 1.65, because it's actually exactly halfway between those two. And if you'll notice, I think the table in your book has a little arrow that tells you to go exactly halfway between those two. So you could actually use any of these three values. Now if you're using your calculator, then here's where we use the inverse norm function. You put in your probability, and then again that has to be in the left end of the graph, so we'd use the 0.95, 0 and 1 since we're doing z-scores. And this is going to give you something like 1.64 if you round it to 2 decimal places. So what that tells us is that if our test statistic comes out to be 1.64 or greater, then our conclusion will be to reject the null hypothesis. So if it's over here, we'll reject the null hypothesis. If it's in this part, then we'd fail to reject. Here's another problem. In this one, we had an alternative hypothesis that p was not equal to 0.4. And again, anytime that we have a not equal to, that automatically tells us we have a two-tailed test. So what we're going to do with our significance level this time is divide it in half and put half in each tail. So we would take our 0.01, divide it by 2, which gives us 0.005, and then that means that we want an area of 0.005 in this tail and an area of 0.005 in this tail. And we need to know what both of these cutoff values are going to be. And remember again that this is a symmetric distribution, so if we find this one on the left side, it will be negative, and all we have to do to get the one on the right side is just take the negative off. They'll be opposites of each other. So the easiest one to find here is the one on the left end, because that's how our table works already. So in our table, we're going to look up 0.0050 in the middle of the table. We're going to find the value closest to that and then find the corresponding z-score that goes with it. Now with your calculator, you would do inverse norm, put in your 0.005 and 0 and 1. Again, this is going to give you a negative value. Either one of these two will. So what we're going to get from either one of these is approximately negative 2.58. So that means that one of our critical values is negative 2.58. The other one would be a positive 2.58. What that means is if our test statistic comes out to be either less than negative 2.58 or greater than a positive 2.58, then in either case we'd reject the null hypothesis. So if it's over there or over there, we'd reject the null hypothesis. If it's in between, in the middle here, then our conclusion would be fail to reject the null hypothesis. Now the other method is called the p-value method, and in this case all we do is find our test statistic, and then we find the probability that our sample data would be that value or more extreme than that, so that it would be either there or further out in the tail of our distribution. So again, this depends on which type of test we have. If we have a left-tailed test, then our p-value is going to be the area to the left of our test statistic. If it's a right-tailed test, it will be the area to the right of the test statistic. And if we have a two-tailed test, then we find the probability of whichever tail the test statistic is in, and then we double it. And one thing, it's easy to confuse a p-value with a proportion. And just so you know, when we talk about a p-value, we'll always be using an uppercase p. This stands for probability. And if we're talking about a population proportion, the p will be lowercase. All right, so let's look at finding a p-value in this case. We already have our test statistic that z equals 3.21. So let's put it on the graph over here. And in this case, this problem is just a little bit different because the claim is that the likelihood of having a baby girl is different from p equals 0.5. That means that our null hypothesis is that p equals 0.5. Our alternative hypothesis is that p is not equal to 0.5. Different always tells you to use not equal to. So this means that we have a two-tailed test. So what we're going to do is first find the probability that z is at least 3.21, so that it's either there or further out in that right tail, and then we'll multiply it by 2 because we have a two-tailed test. So we're going to start out by finding the probability that z is greater than 3.21. So, and remember in your table, since your table goes to the left, if you look up the 3.21, you're going to have to subtract that answer from 1. So we're going to subtract that answer from 1 to get our probability. And if you're using your calculator, then you'd put in 3.21 as your lower bound. You can use 10 for your upper bound since this is a standard normal distribution, and 0 and 1. If you use your calculator for this, you get something that looks like this. I'll just put down a few of the digits here. And at the end of this, you get E negative 4. Now what that means on your calculator, if you're not used to this is actually tells you it's using scientific notation. So this is like saying 6.64 times 10 to the negative 4th. And remember, 10 to the negative 4th tells you to take your decimal place to the left 4 places. So that would be 0.0000664 would be your answer for your probability there. And if you use the table, you would have come up with 0.0007. Now that was just our probability. We're not to our p-value yet because we still have to do the part where we multiply by 2. So with either of those answers, both of them that would round to 0.0007, if we multiply by 2, then we'd get our final p-value of 0.0014. Now since that's a fairly small p-value, that tells us that there is a good chance that the chances of having a baby girl with this new gender selection method is different from 0.5. Here's another example. In this one we have our alternative hypothesis that p is less than 0.4, and our test statistic is z equals negative 2.49. So the less than tells us that we have a left-tailed test. So we're going to graph our test statistic. So here's the negative 2.49. Since we're doing a left-tailed test, we're going to look at going from that value to the left and what's the probability or what's the area of that region. So we want the probability that z is less than negative 2.49. So again, with your table, you can just look up the negative 2.49. Because we're already going to the left. With your calculator, you're going to have to put in a lower bound, something like negative 10, with your normal CDF function. So if we put in the negative 10, the negative 2.49, from the calculator you're going to get 0.0064. if we round it to 4 decimal places. Now since this was a left-tailed test, this is our p-value. We don't have to multiply by 2. That's only with a two-tailed test. So we could say our p-value is 0.0064. Now for the conclusions, for our initial conclusion, we're only going to have one of two. It's either reject the null hypothesis or fail to reject the null hypothesis. And the way we make that decision with our p-value method is that we compare our p-value to our alpha, our significance level. If the p-value is small, in other words, if our probability is small, if it's smaller than alpha, then our decision will be to reject the null hypothesis. So this is with a smaller p-value. If our p-value is larger than alpha, then we fail to reject. And again, this is because what we're looking at is what's the probability that a result like this would just happen by chance. If that probability is very small, then we have to assume that it didn't just happen by chance. Okay, and we already talked about this, but with the traditional method where we're looking at critical values and critical regions, if the test statistic is in that shaded region that we shaded for our critical region, then we reject the null hypothesis. If it's in between, then we fail to reject the null hypothesis. And finally, we always want to conclude our hypothesis test with a written out statement about what our conclusion is in terms of the original claim. Okay, so here are all the steps we're going to go through for a hypothesis test. We've already talked about all of these. So first we identify our two hypotheses. We identify our significance level, alpha, which will usually be given to us in our problems. We calculate our test statistic. Then with our traditional method, we would identify our critical values. With the p-value method, we'd find our p-value. And then we're going to either compare our p-value to our alpha or look at where our test statistic is compared to our critical values to find our initial conclusion in terms of our null hypothesis. And finally, we'll state our final conclusion. And again, we want this to be an actual sentence in English that says what the conclusion of our test is, whether we do or don't have enough evidence to support our claim. And we also say what the claim was in the first place.